Hi everyone. Well, we were looking at relative frequency distribution, and we were looking at this particular example where we had a frequency divided by the sum of the frequencies. So when we sum the frequencies, it give us 50. So 11 out of 15 times 100. That would give us the relative percentage of the frequency distribution. So a relative frequency distribution or a percentage is each class frequency is replaced by a relative frequency or by a proportion or percentage. So meaning it's going to be replaced either by a fraction or a percent. So it's either going to be replaced by a proportion, which is a fraction, by a fraction, or a percent. So the sum of the percentages should be very close to 100%. So after I calculate 11 out of 50 times 100, 24 over 50 times 100, when we add those values, we should get a total of 100%. Again, there's some wiggle room for rounding errors. We also have the cumulative frequency distribution, which is the frequency of each class is the sum of all of the frequencies. We're looking at less than 125, that's 11, less than 175, it's 35. So where are we getting those numbers? So if we have 11, we have, for the first set, we have 11, then we have 24, then we have 10, then we have 3, then we have 2. 11 plus 24 will give us 35. 20, and then 35 plus 10 would be 45, plus 3 would be 48, plus 2 would be 50. So first we have 35 because 11 plus 24, and then I add 10, I get 45. I add 3, I get 48. I add 2, and I get 50, which 50 is my number of total frequencies when I add them. So what the cumulative frequency does, it tallies up. So the cumulative frequency distribution is actually a tally of all the previous classes. So again, we started with 11 plus 24 gave us 35. And then I added 10 to that. And then we added 10, we got 45, then we added 2. So then we added 3, and then we got 30, and then we added 2, and then we got 50. So remember, these are the frequencies from each of the classes previous to that. So what we do is when we're using critical thinking to use frequency distribution to understand the data, is that what we have is a normal distribution. So we are interested in determining whether something is normal or not normal. And what does that mean? The frequencies must start low, as it's increase, and then 1 or 2 high frequency and then decrease. So for example, in order to have a normal frequency, you start low, and then you have and then you increase 1 or 2, and then you decrease. So start slow, up, and then down again. What is the key? It has to be approximately symmetric. So there should exist some symmetry. So symmetry is the key for a normal distribution. Because frequencies preceding maximum frequency should be probably in a mirror, those follow a maximum frequency. So again, we're starting slow, you have some high, and then we go back to low. See how there exists this symmetry. Again, you start low, we have a peak, we have an increase, and then we go low again. Now there exists the presence of gaps that can show data from 1 or 2 populations. So the converse is not true, because if you have different populations, that does not necessarily mean you have gaps. So there could be presence of gaps that shows in our data. That's because they're coming from 2 or more different populations. Okay. That's where a gap can show up. So let's look at this example. Exploring what does the gap tell us? So this table shows us the distribution of the weight of randomly selected pennies. So here is the weight of the penny. I'm looking at the frequency. So for example, most of the weight we would have a frequency distribution. We had 18 and 19. This is how much pennies will weigh. And then here we had 2, 25, and 8, where this weighted more. And this weighs less. So what happens in between? So notice that here, there's the absence of a gap. So what does this tell us about it? Well, before we know that pennies were made out of a different type of material and a different type of ply. So here, the examination of frequencies here that they reveal a large gap between the lightest pennies and the heaviest pennies. This suggests that we have two different populations. Pennies, when they were made before 1983, were from copper and 5% from zinc. Now, after 1883, 2.5 were made out of copper and 97.5% were made out of zinc. So remember, zinc versus copper and their weights. And here we have two populations, two different populations with respect to time. So then that's where we see identify the gap of what happens to the zeros, the lightest penny and the heaviest. Now we're going to look at some comparisons. We're going to be combining two or more relative frequency distributions in one table, where it makes a comparison of data much easier. So having a graph, having a relative frequency distribution allows us to do comparisons. So having a relative frequency distribution allows us to compare different data. So let's look at the following. If we're looking at this example 4, when we're comparing the times that it takes McDonald's versus Dunkin' Donuts, the table shows the relative distribution for the drive-through length. So for McDonald's and Dunkin' Donuts. So the times it takes for 22%, like between 25 and 74 seconds at Dunkin' Donuts, versus when you're at Dunkin', it's going to be at McDonald's 22% versus 4%. Here, it's going to be taking a much longer time, McDonald's, to have their food ready other than Dunkin', because, well, first of all, McDonald's doesn't have any percent, so here's no percent of McDonald's that would take anywhere between 25 to 74 seconds to get your food ready and during lunchtime. Right, so whereas in Dunkin' Donuts, you can see that there's more efficiency. And also, of course, they're more limited in supply of foods. And you're not ordering a big lunch at Dunkin' Donuts where you are at McDonald's. So then you can do an easy comparison. When you can make an easy comparison when you have two relative frequency distribution. So the two relative. Again, this is relative distribution because we're looking at a percent. So because of the dramatic differences in their menus, we might expect that times will be different. And again, having those relative frequencies make it much more easier to do.